Hey everyone, this is a video lesson that I'm using in my AP Calculus AB class, and I'm putting it online in case it would be helpful to others as well. In this section, we are going to discuss derivatives of exponential and logarithmic functions. I'm really excited to be making this video lesson, not only because I really do like to talk about derivatives of exponentials and logs, but also because it is the last section of Chapter 3, which means when we're finished with this section, we will have seen all of the different derivative rules and formulas that we need to be able to use to move on to the next unit, which will be applying derivatives in problem-solving situations, which I cannot wait for. Plus, it's always just kind of fun to be at the end of a unit, right? Maybe not, because that means you have a unit exam coming up. But okay, let's just not worry about that, and let's talk about derivatives of exponentials and logs today. Before we move away from this title slide, I would just like to mention that it is one of my favorite title slides of the year because of the picture that you see in the background here. Can you guess what that is a picture of? I'm going to tell you, peaches. And not only peaches, but, look at this fuzzy stuff, moldy peaches. And that just makes me think of that one song. Did you ever hear it? It's like, moving to the country, gonna eat a lot of peaches. No? Millions of peaches, peaches for me. Okay, I'm gonna stop. But I hear that song when I see this picture. And the reason I have a picture of moldy peaches is because mold grows exponentially, right? So that is just so fun. All right, let's go. You can find a link to a printable set of guided notes in the description of this video, and that might be a good thing to look at as we work through the different parts of this video lesson. Okay, the first part of this video lesson is just a little review of exponentials and logs. So let's talk about exponential functions. You see here just a standard form of an exponential function, y equals a to the x. We would say that that is exponential function of base a. And the first thing that you need to know is that whenever you see me say base a, or I should say you hear me say base a, that is standing for a number. A is any number. So this could be y equals 2 to the x. This could be y equals 10 to the x. It's any number. And exponential functions model growth and decay, right? Like moldy peaches, growing mold. A very frequently used exponential function is y equals e to the x. You may be familiar with that one. And I know I just said that a is supposed to be a number, but let's not forget that e really is a number, right? It is, I had a professor in college that used to say this, and so I'll never forget what e is, at least these digits. He said, I think e is really great, 2.71828. It's then 18284590. I don't know why I remember that much, but I do. So there you have it. Okay, so let's talk about y equals e to the x a little bit more right here. This could be what the graph of y equals e to the x looks like. That could be the graph of many different exponential functions, actually, but let's call it e to the x. And one point in particular that I want to note that it goes through is the point 0, 1. And that is because anything to the 0 power is 1, right? Except 0 itself, 0 to the 0 power, that's still debatable. What is it? 1? Is it undefined, indeterminate? We're not going to go there in this video, but we'll just say anything else except 0 to the 0 power is 1. The domain of exponentials is negative infinity to infinity. However, the range of this function in particular is 0 to infinity, not including 0. That's the range of many exponential functions, unless you have other factors here that would change that. Okay, finally, here's some properties or other information that's helpful to know. And I could have put a whole lot of properties of exponents in here, right? There's all sorts of them. But we've been working with a lot of those properties throughout the year already, so I wasn't going to jam them all in here. I just wanted to highlight one in particular that we will use in a proof a little bit later in this video. And that is if you have a base to a power times another base to a power, then you can combine those powers through addition, right? Finally, this little piece of information here, is just one way that you can define e as an infinite limit. We actually don't use it in AP Calculus AB I just realized that there's something missing. Looks like a negative, but that's supposed to be an arrow. The limit as n approaches infinity. There we go. Of 1 plus x over n to the nth power. Again, that's a way that you can define e. I think it's pretty cool. I'd like to talk about it. I don't really get to talk about it much in this class, but I just tell you that it's out there so that you sort of know that information. The next box that you see on this page is a review box for logarithmic functions. So we say y equals log base a of x. Where'd my cursor go? There it is a base a logarithmic function. And again, a stands for any number. Note that when you see the log button in your calculator, oh look, I have all sorts of stuff in there. When you see the log button in your calculator, it is a log base 10. Okay, so you can use that to solve exponential equations of base 10. For example, if you had something like 10 to the x equals 20, and you wanted to find what is x equal to here. What do you raise 10 to get exactly 20? Well, what you could do is take the log of both sides to get your answer. And this side results in x. You could, if you want to approximate this answer, type it into your calculator because, again, this log is a log base 10. And there you have it. It's approximately 1.301. And so in math class, that's often what we use logs for, right? You know, I often see glazed over looks when I talk about logs, but we like them for things like this. But also, I want you to know that they're used in calculations for chemistry, astronomy, and even seismology. And so there's a lot of cool applications of logs that we don't get to discuss a whole lot. But if you want to see them, they're out there. You can just look them up, Google them. Okay. A frequently used logarithmic function that we're going to use a lot in this section and throughout the rest of the year is the natural log of x. And I noted over here that the natural log of x, which we really usually write as y equals the ln of x, it is the log base e of x, which means it is the inverse function to this one, y equals e to the x. And so you can see that with the graph and the domain and range being switched, the graph being reflected about the line y equals x, and your domain and range, take a look at this, are switched here. Finally, down in the properties / other information, I did put some properties of logs that are helpful at times, especially when simplifying, I guess. We don't really use these that often. I really like this one in particular, the power property of logs. It sort of reminds me of the derivative power rule. And it can explain, you know, for example, why is log base 10 of 10 to the x equal to x? You know, it could easily explain that. And one that we will use in one of the proofs in this video is the change of base rule for logs. So, you know, I'll point that out when we get there. All right, finally, exponential and logarithmic functions are inverses. And so one thing that I want you to note, because again, we use it in a proof, is that e to the ln of x results in x. And the ln of e to the x also results in x. Okay, that's just good information to know as we move on to proofs of these derivative formulas. So what you see here is a little table where you'll fill in all of the different derivative formulas that we're going to see today. The derivative of e to the x, which is a super cool one. The derivative of anything else to the x, any other exponential. A just stands for anything other than e. The derivative of the natural log of x, we'll see that. It's pretty cool as well. And the derivative of any other log function. Over here, you see the same functions, but with a u instead of x, and that is just to remind you of chain rule. You know, if you have y equals e to the u, and u is some differentiable function of x, we'll just throw that times du over dx in there. like we did when we talked about derivatives of inverse trig functions. Okay, finally, one other thing we need to do before we jump into some proofs, and it is this. We need to know the answer to this limit. The limit as h approaches 0 of e to the h minus 1 all over h. Or I'm actually going to change it for the purposes of using our graphing calculator to the limit as x approaches 0 of e to the x minus 1 all over x. Okay, I'll get the answer to that, and this would be the same answer. And the way that I'm going to do that today is just by approximation. Okay, I think I already have it typed in here. Yes, I do. Look at that. I have e to the x minus 1 all divided by x. Take a look at the graph. As we approach x equals 0 from both the left and the right, it is going toward the same point. There is a hole there. You can see that from the table for sure. See that error there? Okay, however, it does appear that maybe that is the point 0, that hole is at the point 0, 1. So I'm going to say probably this answer is 1. Okay, that stuff that I had in my calculator earlier that I'm going to try to bring up. There it is. Can approximate this answer by, putting in a number that's very close to 0 for the x's. And take a look at this. I get 1. I had 1 coming from the other side of x equals 0 as well. Yep, take a look at that. And again, I get something very close to 1. So we are going to say that this limit is equal to 1. Now, we just approximated the answer to that limit. The way that you actually can find this limit using an exact method is you can change this e to the h to this limit and go from there. Again, we're not going to do that because it takes much longer than what I want this video to be, but that is the way that you can exactly find that this limit is equal to 1. Okay, now we need that information again because what we're about to do is find the derivative of y equals e to the x, and we are going to find it using the limit definition. Remember that limit as h approaches 0 of f of x plus h minus f of x all over h formula. And you will see this limit pop up whenever we work so far through that process. Okay, let's start that process by setting up 2 ordered pairs to do slope, right? The first ordered pair can come from just the x coordinate being defined as x, and that would make the y coordinate e to the x. The second ordered pair can come from the x coordinate being defined as x plus h, and that would make the y coordinate e to the x plus h. Now, y prime will come from the limit as h approaches 0 of the slope between these 2 points, e to the x plus h minus e to the x all over x plus h minus x always just results in h. So what we now want to do is we want to work on evaluating this limit, and when we do that, we will find the derivative of e to the x. Okay, the first step in evaluating this limit is to use that property that I talked about in our exponentials box right here. Okay, but we're going to use it backwards. We have e to a sum, and so we're going to rewrite that as this. And it looks like this. Let's write limit as h approaches 0 of e to the x times e to the h minus e to the x all over h. Okay, so again, we just rewrote e to the x plus h as e to the x times e to the h, and that's just using our, property of exponents, so let's us do that. Now, the reason we do that is because what we can now do is factor an e to the x out of the 2 terms in the numerator. And not only can we factor them out of those 2 terms, but we can take that e to the x out of the fraction and even out of the limit, since the limit is as h approaches 0 and x is not affected by that. Okay, now I'll actually do that in 2 steps though, just so you kind of really understand what we're talking about here. Okay, we have the limit as h approaches 0 of e to the x times e to the h minus 1 all over h. Are we good with that step? So I just factored e to the x out of the 2 terms in the numerator. However, again, what I can also do is I can take it all the way out here. Oops, I just said I was going to take it out of the limit and then I didn't. Let me try that again. I can take it all the way out here. And the reason I can do that is because this is the limit as h goes to 0 and e to the x would not be affected by that. It would not change. So let's take it out of the limit. Finally, we're ready to evaluate because we have the e to the x pulled out and we already know that this limit is equal to what? 1, right? It's equal to 1. Which means we got our answer. Okay, so if y equals e to the x, what we just found was y prime equals e to the x. Oh my gosh, the derivative of e to the x is e to the x. Or another way you could say that is the derivative of e to the x is itself. I think that's pretty cool. Let's note it in our derivative table here. If we have y equals e to the x, what we just found is that y prime is also e to the x. Isn't that crazy? Or please keep in mind that if you have something other than just a plain x, you would say that the derivative is itself. So y equals e to the u. Y prime is also e to the u, but we cannot forget about chain rule. Let me be clear, we cannot forget about chain rule. Kind of sounded like I was saying we can. We can't. So we have to multiply by the derivative of u with respect to x. So we'll just throw in a times du over dx there. Oh my gosh, that's exciting. Okay, the other 3 boxes that you see on this page are proof boxes to do the derivative of a to the x, a being anything other than e, the derivative of the ln of x, and the derivative of log base a. I am going to pause the video right now and fill that information in. And then you can decide how much of it you want to pay attention to. The proofs will reference a lot of this other stuff that I talked about. For example, at some point you'll see a change of base. You'll see a couple of different things. But I'm not going to go over it all in detail because you do not have to prove these derivative formulas on your own. You just need to be able to use them. So again, I'm going to pause now. I'll have that information in, and then you can pause if you want to write it down, after I come back. Okay, I'm back. And as I mentioned, what I did with the next 3 boxes is I already filled them out. This is the proof that we use for the derivative formula for y equals a to the x. I'm not going to go over it in detail. It does use the fact that e and the ln are inverses in here with a rewriting. And then it uses the power property of logs. And then we actually use the fact that we know this formula now to find the derivative of this. Okay, but again, I'm not going to go over it in detail. If you would like to pause it and write all of that down, you can. It is just a proof, though, of this formula, and the most important thing we need to gather from it is the formula. The derivative of y equals a to the x can be written as y prime equals a to the x times the ln, that's a times, the ln of a. Okay, or in u form, we can say it is y prime equals a to the u times the ln of a times du over dx. Now, on to the derivative of the natural log. What we use to prove the derivative of the natural log is we rewrite it as an inverse e to the y equals x function. And then we use implicit differentiation, again, using the fact that we know the derivative of e is itself. And then it just takes a little bit of solving and rewriting to get this. The derivative of the natural log is actually not a really complicated derivative formula. You'd think it might be because logs just seem kind of complicated, right? But the derivative formula is just 1 over x. I think that's kind of cool. So again, the most important thing that we need to take from that information that we had in the box was the formula itself. If y equals the ln of x, y prime is 1 over x. Or in u form, if y equals the ln of u, then y prime is 1 over u times du over dx. And finally, the last box here, y equals log base a, it uses the change of base rule with then the fact that we know that the derivative of the ln of x is 1 over x. And from that information, we get this derivative formula for the log base a. It is y prime is 1 over x times the ln of a. And we will put that information right here. I'm going to be honest, I don't think that one's super cool, kind of annoying at times, but it is what it is. Again, it is 1 over x times the ln of a. Or in u form, it is 1 over u ln of a times du dx. All right, so this box is the most important thing that we've really touched on so far, because these are our derivative formulas for exponentials and logs that we will need to be able to use moving forward. And moving forward, what we're now going to do is we're going to refer to these formulas to differentiate some different functions in our example section. Okay, so take a look at example 1. It says find the derivative of y equals x cubed e to the x plus x. Okay, now that we know that the derivative of, let's go with purple, the derivative of e to the x is itself, we can easily find y prime, dy dx, whatever you want to call it, the derivative of this. But we need to keep in mind that we have other rules that we will have to reference at times. Like right here, we are going to use product rule. Right? We have a product of two functions there. So let's use product rule to start, which is 1 d2 plus 2 d1. And that will give us x cubed e to the x, because the derivative of e is itself, plus e to the x times 3x squared. Add on to that the derivative of x, which is just 1, and you're done. Ooh, not so bad, right? Okay, let's take a look at another example. This says differentiate e to the x squared plus, or I'm sorry, x plus x squared, and for that we will want to use our e to the u formula, which says that if we have a differentiable function of x, we need to remember to multiply by the derivative of it in this formula, which is just itself again. So that means that, well, for example 2, we will write the derivative as e to the x plus x squared. Always just start by rewriting the e function. And then we need to multiply by the derivative of x plus x squared, which is 1 plus 2x. You could put a box around that, call that your final answer. However, sometimes we like to write the polynomial part in front of the e, like this. This is probably more likely how you would see it as an answer. Again, not so bad, right? These derivatives are okay. Let's keep going. Okay, what we see in example 3 are exponentials that are not base e. And what you just need to keep in mind when you're differentiating a function that's not base e is you need to throw in a factor of the ln of the base to your derivative. So for example, example 3a, the derivative of y equals 5 to the x is 5 to the x, still itself, but times ln of 5. You could throw that ln of 5 in front if you want to. That's up to you. The derivative of 5 to the 3x plus 1 is 5 to the 3x plus 1, ln of 5 again, but then don't forget to multiply by an extra 3 because the derivative of 3x plus 1 is 3, and there's your chain rule. Okay, be really, really careful here. This times 3, like, do you want to put it over here? I don't know, because then you might be tempted to multiply it with the base 5, which would not be correct according to order of operations. So I would suggest just leave it like that. Here's your answer to example 3a. Good enough. Here's your answer to example 3b. Let's look at some log examples now. Example 4, find dy dx for y equals the ln of 2x plus 5. Okay, so we're going to use our ln of u formula here because we don't just have an ln of x, we have an ln of something more. And so our ln of u formula says y prime comes from 1 over the u, whatever's in here, you put 1 over it in the derivative, and then don't forget to multiply by the derivative of it. So let me show you what that looks like right here. Dy over dx equals 1 over 2x plus 5. That's the u. And then we multiply by 2. Now, typically we do simplify, I guess you could call it these, by putting this 2 in the numerator, multiplying it with the 1, and making that 2 over 2x plus 5. Example 5, find the derivative of x squared times the ln of x. Here we just have a plain ln of x, but we need to remember to use product rule again, right? There's another product rule. 1 d2 looks like that, plus 2 d1 looks like that. Okay, right here, x squared times 1 over x, we can make that x squared over x, or just x, right? X squared over x, we can just make it x. And then ln of x times 2x, we will write that 2x in front of the ln, just so that we're not tempted to multiply it with the x that's in the ln. And there's your final answer to example 5. Okay, examples 6 and 7 are now going to use the other log formulas. We can call this, please keep in mind again, if you do not see a base on the log, we are going to assume it is a base 10. So why don't we just write that in there? This will be a base 10. And here we see a log base 2. And so again, what we need to reference for those examples is our log base a of x formula, or really, I think for both of them, yes, we will need to use this one, log base a of u. Okay, so this is the one where students sometimes have trouble. So I'm going to first write the formula. Again, the formula is if I have log base a of u, not equals, I'll say if y equals log base a of u, then y prime is equal to 1 over u times the ln of a. That ln of a is in the denominator with the u, and then times du dx. Okay, so let's try to follow that with this example. This is the u, what is inside of the log, which is the square root of x. So we're going to start with 1 over the square root of x. Don't forget the ln of your base here, which in this case would be the ln of 10. We'll then multiply by the derivative of the square root of x, which is 1/2 x to the negative 1/2, just using power rule, right? Because the square root is a 1/2 power. You could leave your answer like that, honestly, and it'd be fine. You know, it'll get the job done, I'm sure. However, we could simplify it to this. All of this stuff can go in the denominator with this stuff because we have 2 down here. We have an x to the negative 1/2 power, which is a square root of x in the denominator, where we have another square root of x already hanging out there. Okay, does that make sense? This 2 goes down into the denominator. This x to the negative 1/2, that's a square root in the denominator, but there was already another square root in the denominator. So finally, you can put those pieces together. Root x times root x is just x, and it simplifies kind of nicely So 1 over 2x times the ln of 10. Okay, the simplifying was probably more tricky than applying the formula. And again, don't worry about simplifying so much right now unless we need to. What's most important is that you're able to apply your derivative rules. Finally, example 7, find dy over dx for y equals log base 2 of x to the 4th. Okay, that would look like this. This time the u is x to the 4th, so it is 1 over x to the 4th times the ln of 2, because that's the base that I see right here, times the derivative of x to the 4th, which is 4x cubed. Now let's at the very least put that 4x cubed in the numerator. But then what you'll probably be tempted to do, and you can because we don't see any other terms here in the numerator, you could cancel all of these or divide out this x cubed with 3 of them here and write a simplified answer as 4 over x times the ln of 2. All right, one more time though, if this simplifying stuff confuses you, just for now, focus on being able to do your derivatives, get the hang of that, and then maybe later on the simplifying will come when you need it. Okay, where we might need a little bit of simplifying is here with example 8. Let's see. The question is, at what point on the graph of the function y equals 2 to the x minus 3 does the tangent line have a slope of 21? Okay, so in no place does it say to differentiate. However, it is asking us for one particular point of a given slope, and so that means we do need to have a derivative formula to answer that, right? So let's just do that first. Let's get y prime of this function, and that will give us our slope formula. And it's pretty easy. The derivative of 2 to the x is 2 to the x times the ln of 2. Right? That's using our y equals a to the x derivative formula. The minus 3 goes to 0, so that's it. Okay, now this slope of 21, that's giving us a particular y prime value. To 7. And so now what we see is that we have an equation where we need to solve for x. Okay. Solving for x, let's just first flip it around. I don't know, it just kind of bothers me. I'm going to move it over here. Especially when it's like kind of complicated to solve. Let's make sure that we have what we're solving from on the left and where we're moving things to on the right. And now the first step is to divide both sides by the ln of 2. So we'll have 2 to the x equals 21 over the ln of 2. And I'm just going to leave it like that. And then from there, we need to solve for the x by taking the log base 2 of both sides. Like that. Log base 2 of 2 to the x results in x being by itself. And what we have on the other side is log base 2 of 21 over the ln of 2. All right, finally, it's like, how do we get an answer out of that? Because remember, this button in our calculator is not a log base 2. We can't just type that in. That is a log base 10. Okay, well, we could write it as a log base 10 if we use the change of base rule. And the change of base rule would look like this. I'll move this up here. We could say, let's take the log base 10 of all of this stuff over the log base 10 of this base. We could type that into the calculator. And we have an approximate x value now, 4.921. Okay, so to get an approximate answer that actually kind of, is a number we can make sense of, we did need to use a log rule here, the change of base rule. However, if you didn't have that, or if you didn't have a calculator, you would just leave your answer in this form. Okay, that's not my favorite application, I'm going to admit, but the last two applications we see here in this notes set, I really like. Let's take a look at this one. A Cessna plane takes off from an airport at sea level, and its altitude in feet at time t in minutes is given by this equation, h equals 2,000 times the ln of t plus 1. We are finding the rate of climb at the instant t equals 3 minutes. Okay, so first of all, I just want to show you what a Cessna plane looks like. Cessna plane. Okay, here's some pictures of a Cessna plane. Nice, right? All right, there we go. Now we have a cute little picture in our head. And this formula is showing us its altitude at any given time. Okay, since we're asked to find the rate of climb, let's use red because some of those Cessna planes had red on them. Find the rate of climb. That means what we are going to want to find first is h prime. Okay, and to find h prime, we are going to take the derivative of the ln of t plus 1, carrying along a constant multiple of 2,000. That 2,000 can just come down, and the derivative of the ln of t plus 1 is 1 over t plus 1 times the derivative of t plus 1, but that's just 1, right? The derivative of t plus 1 is just 1. So our h prime formula, we can even call this h prime of t if we want to, is 2,000 over t plus 1. Now, in particular, we were asked to find this rate at the instant t equals 3 minutes. So finally, what we want to do is sub in 3 for t. And what do we get out of that? 50? Oh, no. 500. 500 feet per minute. Right? Yes. Okay, there we go. All right. So, a cute little example there of finding the rate of a plane climbing from sea level with a derivative of a natural log. Okay, finally. This one's going to hit a little too close to home, unfortunately, this year in 2020. Take a look at example 10. Okay, the spread of a flu in a certain school is modeled by this equation, where P of T is the total number of students infected T days after the flu was first diagnosed. In part A, we are to estimate the initial number of students infected with the flu. In part B, we are to find how fast the flu is spreading after 2 days. And in part C, we will find when the flu is spreading at its maximum rate and what that rate is. Okay, so let's do this. Talk about real life situation here. Remember, this is our function that tells us the total number of students that are infected at any given number of days. T stands for the days after the flu was first diagnosed. In part A, estimate the initial number of students. What I want you to think about is, do you need a derivative to answer part A? Remember, whenever you see keywords like rate or slope, that's when you need a derivative. Are you asked for any of that here in part A? No. You are just asked to estimate the initial number of students who are infected. And so that would just be the function value when t equals 0. Or, why don't I write it like this? Initial means t equals 0. So initial number of students means what we are finding is P of 0. Does that make sense? So let's find P of 0. That means subbing in 0 where you see the T. And we are just going to do an estimate of this in our calculator now. Make sure you use parentheses around your denominator. 1 plus e to the 3, right? 3 minus 0 is 3. So the initial number of students is 4.742, 4.743, or we could say approximately 5 students. So again, what I want to highlight there is that you did not need to find a derivative because you didn't see anything asking you about its rate of spread. Just initial number of students means use the original function given. However, in part B, notice that the question is now how fast is the flu spreading? And because of that indication of a rate, in particular, we're looking for after 2 days, we do need to find now P prime. Or here, after 2 days, it's going to be P prime of 2. No, what just happened? Everything went crazy. Because I hit a button by accident. Okay, so first let's work on finding P prime of T, and then we will sub 2 in. The way that you're looking at your P of T function right here, it is a quotient, and so we would need to use quotient rule. However, we could, because this is just a constant up here, we could write this, we could rewrite it, I should say, as 100 times the quantity 1 plus e to the 3 minus t raised to the negative 1 power. And then that would eliminate the need for quotient rule. And we would not have to do product rule because this is a constant multiple of 100. So all we would need then is chain rule with power rule, right? I think that's the way that I want to go with this. So again, what I did up here was I took this 1 plus e to the 3 minus t. I moved it up to multiply it with the 100. And to do that, I needed to put a negative 1 power on it. And so now I'm going to focus on that negative 1 power to get my P prime using power rule. The negative 1 comes down and multiplies with the 100, making it a negative 100. Rewrite what's in the parentheses and raise that to the negative 2 power because negative 1 minus 1 is negative 2. Then we'll multiply that by the derivative of what we see here. The derivative of 1 plus e to the 3 minus t. Okay, the derivative of 1 is 0. The derivative of e is itself. But don't forget to multiply by the derivative of 3 minus t, which is negative 1. Okay, so now I'm going to put that back into quotient form. I have a negative 1 times a negative 100, which takes that back to a positive 100. And the other thing that I'm going to have in the numerator is this, e to the 3 minus t. This set of parentheses will move to the denominator because it is a negative 2 power. And when we move it to the denominator, it can become a positive 2 power. All right, so that was the trickiest part, by the way, of this whole entire problem, getting that derivative. And again, if you didn't like what I just did there with chain rule, you didn't have to rewrite. You could have left it in this form and did quotient rule, low d high minus high d low over a low low, and simplify a little bit, and you would get the same thing. Okay, finally, let's do P prime at 2. And that means changing all of the t's that we see to 2's, which kind of leaves us with a cool thing because 3 minus 2 is 1. Sorry, it like did a little freezy thing there. And I will go to the calculator to finish that. So let's see, I have 100 times e to the 1 divided by 1 plus e to the 1 all squared. And from that, I get approximately 20, say 19.661. Or we could say approximately 20. And what's the units here? Well, it's number of students per day, right? Since P was defined as students infected, and we're doing the rate with respect to days, this is students per day. dy. I just wrote dy. Students per day. There we go. Okay, finally, in part C, we are asked, when will the flu spread at its maximum rate? What is this rate? Okay, we're going to talk a whole lot about finding maximums and minimums in the next unit and how you can use derivatives and different derivative tests to do that. However, for right now, we're being asked for the maximum rate of spread. And so what we can do is graph our rate function, which would be our derivative graph, and just find the highest point, with the graphing calculator. So I already went ahead and put the derivative formula in terms of x into my calculator. So what we wrote right here, 100 e to the 3 minus t over 1 plus e to the 3 minus t quantity squared. That's what I, am going to graph here, and I typed it into my y equals on my calculator. And when I look at the graph in a standard viewing window, I can see that it goes up, and the maximum point is somewhere up here, but I'm not seeing it in a standard viewing window. So we could look at the table and investigate the function values. Whoop, I think I found it. Let's take the y max up to, let's say 30, just to go a little bit higher than the highest y coordinate that I was seeing in my table. Okay, take a look at that. Okay, remember when they're talking about flattening the curve from COVID? Okay, this is what they mean. It goes up to be spreading at its maximum rate, and then it stops spreading at its maximum rate and goes down. Okay, that's just something that's not happening for us right now, but hopefully it will be soon. Okay, and so what we want to find right now is that maximum point. So I'm going to go into my calculate menu, second trace in the calculator. I'm going to choose option number 4, maximum, and then I just have to answer those 3 questions. What is the left bound? Let's move close to the highest point, but stay on the left of it, hit enter. What is the right bound? Move right until you're past the highest point, hit enter, and then enter one more time to guess. And here it is. The maximum rate is going to be at 3 days, and the rate is 25 students per day. Okay, so we'll put that information right here. When will the flu spread at its maximum rate? We'll just sketch a little P prime of T versus T graph. And again, it looks something like this. And we found that when t equals 3 days, it was spreading at its maximum rate of 25 students per day. So let's just say that at t equals 3 days, the flu is spreading at its maximum rate of 25 students per day. I did it again. I wrote dy. I think I'm just like thinking about dy over dx. I don't know. Students per day. There we go, brain. All right. Yay, we're done. So I just think I love ending with that example because especially right now, it is a very real life application of exponential functions and their derivatives. Remember, the derivatives help us to find how fast something is spreading or, its rate. Okay, everybody, as usual, I hope this was helpful and good luck in your studies. Bye.